Question number 21. A conducting square loop of side L and resistance R moves in its plane with the uniform velocity V perpendicular to one of its sides. A magnetic induction B constant in time and space pointing perpendicular and into the plane of the loop exists everywhere as shown in the figure. The current induced in the loop is option 1 BLV by R clockwise, option 2 BLV by R anti-clockwise, option 3 2 BLV by R anti-clockwise, option 4 0. This is the diagram given. So we have to see the solution. This is the key given. Question number 21. The answer for this question number 21, correct option is option 4. Current induced is given by the formula I is equal to, it is actually modulus of E by R, magnitude of E by R. So this is simply magnitude of E, okay, by R, because we know I is E by R, Ohm's law. Now again this magnitude of E is d phi by dt, Faraday's laws. This is Faraday's law. Okay, but here there is no change of flux. D phi is change in flux. D phi by dt, here it will be rate of change of magnetic flux, but there is no change of flux with time in this case. Why? Because you see he has given very clearly in the question, a magnetic induction B constant in time and space pointing perpendicular and into the plane of the loop exists everywhere. That means you can see the field is existing everywhere. This side also, okay, here also, even above, the field exists everywhere. So all the time the magnetic field with the loop is constant. B is constant. B is constant, both in space and time it is given. So flux is constant. Flux is constant because phi is BA, here theta 0, BA cos theta, cos 0 is 1, so phi is BA. B is constant, area is also constant. All the time the coil is fully inside the magnetic field. He said the field exists everywhere, that is important. See here, in case 1 here, the coil enters into the field region. Non-field region to field region, if the coil enters, the flux will increase. Here the coil goes outside the field. From the field region to no field region, the coil moves. So here also the flux changes. Here the flux increases, here the flux decreases. But so long the coil moves fully within the magnetic field, the flux is constant. It is all the time in the field region, right? So case 1 flux increases, case 3 flux decreases, but case 2 flux remains same. Same thing here, flux remains same, phi is constant. Therefore there is no induced EMF. Therefore there is no induced current. Correct option is option 4. Question number 22. The magnetic flux linked with the coil, of course the unit is Weber, is given by the equation phi is equal to phi t square plus 3t plus 16. The induced EMF in the coil at time t is equal to 4 will be 4 seconds, it should be 4 will be option 1 minus 27 volt, option 2 minus 43 volt, option 3 minus 108 volt, option 4 210 volt. This is the answer given in the key. Given phi is equal to 5t square plus 3t plus 16. Induced EMF V is equal to, of course first he has taken magnitude, then again he has introduced negative symbol, right? So you need not take magnitude, straight away you can say E as minus d phi by dt, right? E as minus d phi by dt. So this negative symbol is there all the time, okay? Minus here, and of course fully minus here, so minus here also, right? So d phi by dt, so minus d by dt of 5t square plus 3t plus 16, which is 10t plus 3. So just to take only the induced EMF without the magnitude, so minus symbol will be there. Put t is 4, 10 into 4, 40 plus 3, 43. If you do not take the magnitude, it will be minus 43 volt. Correct option is option 2, minus 43 volt. Question number 23. Which of the following graphs represents the variation of current I with frequency f in an AC circuit containing a pure capacitor? 4 diagrams are given. Option 1, option 2, option 3, option 4. Correct option is option 3, this one. This is the explanation given. I is equal to V by Xc. Here Xc is capacitive reactance. Xc is 1 by C omega. C omega is 2 pi f. So 2 pi f into C. This will go to the numerator. So V is equal to 2 pi f into C. So I is proportional to f. Because V constant, 2 pi constant, capacitance is constant. I proportional to f. Other parameters are constants, kept constants. So it is I proportional to f graph, or I is equal to kf graph, which is a straight line. So that comes as option 3. So we have the correct option as option 3 here, okay. Question number 24. A 20 volt AC is applied to a circuit consisting of a resistance and a coil with negligible resistance. So this is a coil, that is an inductor with no resistance, ideal coil. Then if the voltage across the resistance is 12 volt, the voltage across the coil is option 1 16 volt, option 2 10 volt, option 3 8 volt, option 4 6 volt. Okay, this is from the key. This is a circuit, 20 volt AC, circuit consisting of a resistance and a coil. This is a coil, this is a resistance. Both look similar. This is coil, this is resistance. Because he has given VL no here, so this has to be coil. This is resistance, right? Okay. So how do you do that? We know that V is equal to root of VR squared plus VL squared. In the case of, this is an LR circuit. LR circuit. Therefore, V is equal to root of VR squared plus VL squared. This step is not necessary. Okay. So 20, net voltage is given to be 20 here. Root of VR squared, VR is given 12. We are supposed to find VL. So 20 square is equal to 12 square plus VL squared. So VL squared is 20 square minus 12 square. We want VL, no? So 20 square minus 12 square. So 400 minus 144, root of 256, which is 16 volt. See, correct option is option 1. Direct problem. Question number 25. The instantaneous values of EMF and the current are. Question number 25. The instantaneous values of EMF and the current in a series AC circuit are E is equal to E naught sin omega t and I is equal to I naught sin omega t plus pi by 3 respectively. Then it is option 1 necessarily an RL circuit, option 2 necessarily an RC circuit, option 3 necessarily an LCR circuit. Of course it is series already given. Option 4 can be RC or an LCR circuit. Answer for this question number 25, option 4. E is E naught sin omega t given, I naught sin omega t pi by 3 given. Correct option is option 4. What is the reason given? As current can lead the voltage in RC and LCR circuit, it should be or it can be RC or LCR circuit. So option 4 is correct option. See here, instantaneous values of EMF and the current. Value of EMF E naught sin omega t. Instantaneous value of current I naught sin omega t plus pi by 3. You see here there is plus pi by 3, which indicates current leads. Current leads. Here only omega t, here omega t plus pi by 3 current leads. So leading current is given by only a capacitor in a circuit. Inductor means it will produce lagging current. So there should be a capacitor. Then only capacitor is there. This should be pi by 2 plus pi by 2. If you remember the phasor diagram, you will agree. But it is not pi by 2, but it is something else, pi by 3. Therefore, in addition to capacitor, there should be a resistor, or there can also be say an inductor in addition to the resistor, but capacitive nature should be more, right? That's what is given as the answer. You can refer to phasor diagrams. See, this is a phasor diagram for a CR circuit. CR circuit. This is VR, voltage across the resistor. This is current, which is same for both resistor and capacitor. This is VC. You see current here. This is the net voltage. Okay, this is the net voltage. Of course, arrow is there. This angle is the phase angle. Now you can see current leads the voltage by here some angle, but question it is given pi by 3 in units of radian. So it is possible for a CR circuit. Not only that, if it is an LCR series circuit, this is the phasor diagram for LCR, of course series circuit. Here this is a category of XC greater than XL. That is important. This is current, this is voltage across the resistor, all RMS values. This is VL, this is VC. See, VC is all the way from here to here, very long. VC greater than VL. This will be VC minus VL. That means this one is VC minus VL. This angle is the phase angle. It can be pi by 3 also. It can also be pi by 3. So current leads the voltage. This is the voltage by an angle of pi by 3 in terms of radiation. Pi by 3 in terms of radians. Therefore, it is possible to have a phase angle of pi by 3, current leading the voltage in just a CR circuit or even in LCR circuit where XC greater than XL. So the correct option is option 4. Okay.